I need to start by telling you about one of the greatest misunderstandings in human history. And it's not a small misunderstanding like, I thought the event was on Thursday, but it was Friday. It's a misunderstanding so profound, so fundamental, that it has shaped centuries of how we think about knowledge, truth, and the very nature of reality. The misunderstanding is this. People think that when one scientific theory is replaced by another, it means that the first theory failed or was wrong. Newton was wrong. Einstein proved it. Right? Wrong. Completely wrong. And understanding why this is wrong will change the way you think about practically everything. Let me explain. Isaac Newton published his theory of universal gravitation in 1687. He stated that every object with mass attracts every other object with mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. F, G, M1, M2, R2. Simple, elegant, and it worked incredibly well. With that formula, you could predict the movement of the planets with absurd precision. You could calculate when eclipses would occur. You could discover the mass of the sun just by observing how the planets orbit. When astronomers noticed that Uranus wasn't behaving exactly as predicted by Newton's theory, they didn't say, "Oh, Newton was wrong." They said, "There must be another planet out there that we haven't seen yet, pulling Uranus." And they used Newton's theory to calculate exactly where that planet should be. They pointed their telescopes there, and bam, they found Neptune. This is physics working the way it should. For 200 years, Newton's theory was one success after another. Then, in 1915, Einstein came up with general relativity. And general relativity makes predictions that differ slightly from Newton's theory. In weak gravitational fields and low speeds, the differences are minuscule. But in strong gravitational fields or at speeds close to the speed of light, the differences become significant. And when they tested it, when they measured the curvature of light from stars passing near the sun, when they measured Mercury's orbit with extreme precision, was Einstein right and Newton wrong? No. And this is where people get completely confused. Newton wasn't wrong. Newton's theory is an incredibly good approximation of reality under certain conditions, specifically when speeds are much lower than the speed of light and when gravitational fields are not extremely intense. Let me give you an analogy. Imagine you're measuring the length of a table. You take a ruler and measure 2 meters. Then, someone arrives with an ultra-precise laser device and measures 2.037 meters. Was your ruler measurement wrong? Well, it wasn't perfectly accurate, but for practically any practical purpose, building a chair, knowing if a table fits through a door, your measurement was perfectly adequate. Laser measurement is more precise, yes, but that doesn't make your ruler flawed or wrong. Newtonian physics is the ruler. Einstein's relativity is the laser. Both give you answers. The difference is the level of precision and the conditions under which they work well. And you know what's most incredible? We still use Newtonian physics all the time. When NASA sends a probe to Mars, most of the calculations use Newtonian mechanics. When engineers design bridges, airplanes, cars, Newton. When you throw a ball and intuitively know where it will land, your brain is doing Newtonian physics. Why? Because it works. It works extremely well for the vast majority of situations we encounter. So here's the first big lesson. Scientific theories are not absolutely true or false. They are tools with domains of applicability. Newton's theory is perfectly valid and extremely useful in its domain. Macroscopic objects moving at speeds much slower than light in relatively weak gravitational fields. Einstein's relativity extends this domain to include extreme situations. And undoubtedly, one day we will encounter situations where Einstein's relativity needs to be extended or modified as well. In fact, we already know of a situation where this happens. Quantum scales in intense gravitational fields. We have quantum mechanics, which works perfectly for small particles. We have general relativity, which works perfectly for massive objects. But we still don't have a complete theory of quantum gravity that satisfactorily unites the two. Does this mean that quantum mechanics and general relativity have failed? No, it means that each has its own domain of applicability, and we need something more for the domain where both are important simultaneously. Now let me show you why this misunderstanding, thinking that old theories are simply wrong, is so problematic. First, it creates a completely distorted view of how science progresses. People think science works like this. Someone proposes a theory. Decades later, we discover it's totally wrong. We throw it away. We start from scratch with a new theory. Repeat. But that's not how it works. It's more like this. Someone proposes a theory that works well in a certain domain. We use that theory extensively, refine our understanding, and make thousands of successful predictions. Eventually, we find the limit of the domain, situations where the theory doesn't work so well. Then we create a more comprehensive theory that includes the previous theory as a special case. Einstein's relativity didn't discard Newton. It encompassed him. When you take Einstein's equations and apply them to the limit of weak gravitational fields and low velocities, you recover Newton's equations. Newton is inside Einstein as a special case. It's like those Russian nesting dolls, the matryoshkas. Each larger theory contains smaller ones. Nothing is discarded. It's incorporated, refined, placed in the appropriate context. Secondly, this misunderstanding leads people to distrust science incorrectly. Have you ever heard someone say something like, "Well, they thought Newton was right and he was wrong. How do we know Einstein is right? Maybe in 100 years we'll find out he was wrong too." This is a fundamentally flawed criticism. Newton wasn't wrong in the way this person imagines. Newton's predictions are still correct in the appropriate domain. And yes, it's entirely possible, even probable, that one day we will have a theory even more comprehensive than Einstein's. But that theory will have to reproduce all of Einstein's successful predictions in the domain where Einstein works, just as Einstein reproduces Newton in the domain where Newton works. Each theory is a better approximation than the previous one. We're not going in circles, throwing everything away and starting over. We're building, refining, expanding. Third, and this is subtle but profound, this misunderstanding leads people to believe that there is a final, true theory waiting to be discovered, and all others are merely false approximations of it. But here's a possibility that should make you stop and think. Perhaps there is no final theory. Perhaps it's all approximations until the end. Think about it. You can describe the trajectory of a ball with different levels of precision. You can treat it as a point without rotation. Very simple. You can include rotation and air resistance. More complicated. You can model the deformation of the ball when it bounces. Even more complicated. You can go all the way to the molecular level, modeling every molecule in the ball and in the air. Absurdly complicated. Which of these is the true description? The question doesn't even make sense. The appropriate description depends on what you're trying to understand and the level of precision you need. Perhaps the universe is like that. Perhaps there is no single, true description, only increasingly accurate descriptions, each appropriate for different scales and contexts. And you know what's craziest? This doesn't make physics any less powerful. It makes it more powerful, because it means we can always find a suitable description for the problem at hand without needing the overwhelming complexity of a theory of everything. Now, let me show you a specific example that really illustrates how we misunderstand the progress of physics. Let's talk about light. For a long time, people debated, is light made of particles or waves? Newton thought it was particles, tiny corpuscles traveling in straight lines. Others, like Huygens, thought it was a wave. In the early 19th century, interference and diffraction experiments seemed to definitively prove that light is a wave. You can pass light through two slits and it creates an interference pattern, alternating light and dark areas, just like water waves would. Case closed, right? Light is a wave. Newton was wrong. Then, at the beginning of the 20th century, other experiments began to emerge. The photoelectric effect, studied by Einstein, him again, showed that light behaves as if it were made of small packets of energy, quanta, or photons. Particles. Was Newton right? No, wait, they were both right, and they were both wrong, or rather, they were both partially right, each capturing a different aspect of reality. Light is neither a wave nor a particle. It is something more fundamental that exhibits wave properties in some situations and particle properties in others. We call this wave-particle duality, but that name is misleading. It's not that light is sometimes a wave and sometimes a particle. It's that light is something that our everyday categories of wave and particle cannot fully capture. And here's the crucial point. When you make certain types of measurements, the wave description works perfectly. When you make other types of measurements, the particle description works perfectly. Neither failed. They are simply different descriptions, appropriate for different contexts. Modern quantum mechanics gives us a more complete mathematical description that encompasses both wave and particle behavior. But even so, in practice, we often use the simple wave description or the simple particle description when appropriate, because they are easier to work with. Does this remind you of anything? It's exactly like Newton and Einstein. The older description isn't wrong. It's a useful tool within its field. Now I'm going to tell you something that many people find shocking. The same thing applies to absolutely everything in physics. In school, you learn about atoms, protons, neutrons, electrons. Cool, useful model. Then you learn that protons and neutrons are made of quarks. Oops, so atoms aren't fundamental then? Was the previous model wrong? No. For most purposes in chemistry, biology, and materials science, you don't even need to know that quarks exist. The model of atoms made of protons, neutrons, and electrons works perfectly. You learn classical physics. Objects have definite positions and velocities. Then you learn quantum mechanics. Objects don't have simultaneously definite positions and velocities until they are measured. Was classical physics wrong? No. For large objects, larger than, say, large molecules, quantum effects are so small that the classical description works perfectly. Nobody uses quantum mechanics to calculate the trajectory of a baseball. Do you see the pattern? In each case, the older theory hasn't failed. It remains a perfectly valid and useful description within its domain of applicability. And this brings us to the heart of what I want to tell you. Physics hasn't failed. We just misunderstand what success means in physics. Success in physics is not about finding the ultimate absolute truth with a capital T. Success in physics is about finding mathematical descriptions that make accurate predictions in specific domains. Newton's theory is a monumental success because it allows for incredibly accurate predictions for a vast range of phenomena. The fact that there are phenomena outside its domain does not diminish this success. It's like saying a hammer failed because it's not good at tightening screws. No, the hammer didn't fail. You're just using the wrong tool for the job. And here's something really important. We don't know if we'll ever have a theory that works in every possible domain. It may be that the universe is fundamentally stratified into layers, each requiring its own description. Imagine a computer simulation. At the lowest level, you have zeros and ones, bits. One level above, you have machine instructions. Further up, a programming language. Further up still, the user interface. You could, in principle, describe what's happening on the screen in terms of zeros and ones. But that would be absurdly complicated and completely impractical. The description in terms of the user interface is much more useful at that level. The universe could be like this. Fundamental particles are one level, atoms are another, molecules are another, cells are another, organisms are another, societies are another. Each level has its own rules, its own appropriate descriptions. And you know what's fascinating? The more we study, the more we find these levels of description. And at each level, there are emergent phenomena, patterns and behaviors that make sense at that level, but would be absurdly complicated to describe at the level below. Consciousness, for example. You could, in principle, describe your consciousness in terms of neurons firing, and you could describe neurons in terms of molecules, and molecules in terms of atoms, and atoms in terms of fundamental particles, and perhaps particles in terms of string theory or whatever is even more fundamental. But would this description at the most fundamental level be useful for understanding consciousness? Almost certainly not. Consciousness is an emergent phenomenon that makes sense at the level of neural networks, not at the level of quarks. So here's the big truth that people don't understand about physics. We're not looking for a single true description of reality. We're building a collection of descriptions, each appropriate for different scales, different contexts, different questions. And these descriptions relate in specific ways. You can derive thermodynamics from statistical mechanics. You can derive classical mechanics from quantum mechanics in the appropriate limit. you can derive Newton from Einstein in weak gravitational fields. This creates a coherent structure where different theories connect and support each other. It's not chaos. It's not, everything is relative, man. It's a carefully constructed hierarchy of descriptions, each validated by countless experiments. Now, let me give you a concrete example of why this matters in practice. Suppose you want to predict the weather for the next week. Do you need quantum gravity for that? Of course not. You don't even need quantum mechanics. You don't really need relativity. Weather models essentially use classical physics, fluids, thermodynamics, heat transfer. Are these models wrong because they don't include quantum or relativistic corrections? No, they are appropriate for the problem. Including quantum corrections would not significantly improve climate predictions. It would simply be a waste of computational power. Or another example, you want to design a computer chip. Now you need quantum mechanics because modern transistors are so small that quantum effects matter. Do you need general relativity? No. Do you need string theory? Definitely not. Use the right tool for the job. That's the real wisdom of physics. And this brings us to something I find profoundly beautiful. Physics is not a building with a single foundation that, if broken, brings everything down. It's more like a network, a tapestry, where each theory connects to others, each one independently validated in its own domain. If tomorrow we discover that general relativity needs corrections in some extreme situation, this does not invalidate GPS satellites that use relativity and function perfectly. It does not invalidate the detection of gravitational waves. It does not invalidate decades of successful predictions. It would simply mean that we have reached the limit of the domain of applicability of general relativity, and we need something more beyond that limit. And you know what's most incredible? It's already happened. We know that general relativity and quantum mechanics are incompatible in certain extreme situations, like the center of black holes or the Big Bang. Does this mean that both have failed? No. It means that each one works in its own domain, and we need a more comprehensive theory for situations where both are important. And while we don't have that theory, we still use general relativity and quantum mechanics with enormous success in their respective domains. So, here's what I really want you to understand. When someone tells you, science has changed its mind about X, so how can we trust science? The answer is, science hasn't changed its mind in the way you think. Science has refined, expanded, and placed it in the appropriate context. The successful predictions of the previous theory are still valid in their domain. They haven't been discarded. When someone tells you, Newton was wrong, Einstein was right, the answer is, not exactly. Newton is correct within his domain of application. Einstein expanded that domain. Both are right in the sense that matters. They make accurate predictions when applied appropriately. When someone tells you physics is just theory, it could all be wrong. The answer is, theories in physics are not wild guesses. They are precise mathematical structures that make testable quantitative predictions. And when these predictions are confirmed thousands of times, the theory gains the status of a reliable tool within its domain, regardless of whether it is the final truth or not. Physics hasn't failed. It's our understanding of what constitutes scientific knowledge that has failed. Or rather, it was poorly taught from the start. Scientific knowledge is not a collection of absolute truths set in stone. It is a collection of increasingly precise models, each with its own domain of applicability, all connected in a coherent network that gives us unprecedented power to predict and manipulate the natural world. And this network continues to grow. There will always be new phenomena to explore, new domains to map, new theories to develop. But each new theory does not destroy the previous ones. It contextualizes them, refines them, incorporates them as special cases. This is how real progress works, not in dramatic revolutions where everything is thrown away and we start from scratch, but in careful expansions, gradual refinements, elegant syntheses that show how apparent contradictions are actually complementary aspects of a richer reality. And when you understand this, really understand it deep down, you stop seeing the history of physics as a series of failures and start seeing it for what it really is, one of humanity's greatest achievements. A demonstration that finite, limited creatures can build reliable knowledge about an infinitely complex universe, not by finding absolute truths, but by building increasingly better tools to understand, predict, and navigate reality. And that, my friend, is not failure. It's triumph.